Okay, we're going to take a look at the Module I PowerPoint here. And so this is going to be on Siemens function blocks. Once again, you would have downloaded the PowerPoint and you would have clicked on the link there for the lecture video. That's why you're watching this. You'll have to stop the video a few times. There's some longer videos linked into here that you'll have to watch, and then you'll have to fill out the lecture video worksheet and then turn that into the lab instructor. The outcomes for this week are to determine what is the primary difference between a function and a function block, what is the purpose of a data block, how are parameters passed in and out of a function block, what is the difference between local and global tags, give a real-world example of a function block, explain the advantages of programming using function blocks. But let's start with a Module 8 review. So in Module 8, we noticed that Siemens allows series outputs. Not only that, you can intermingle inputs with outputs. And so if you think about that, that means that you could turn on a bit, and then instead of having to have a contact associated with that bit that needed to be put back into the ladder to allow it to become true, you could just put the output in there. And then that would cause the rung to continue to be true. And we had a bunch of series contacts and coils, and as soon as the left part of the rung became true, it passed to the right, and then more of the rung became true left, it passed to the right all the way through. So series outputs, you can use them sometimes. Remember, you still only probably want to use an output once, but this can help with the scan time because the early part of that rung can be solved, and then you don't have to worry about solving the rest of it if that's really all that you're looking for. We use some internal relays, which are M, and what you want to remind you of on that is that we used energize. We energized a bit, and then if that bit was high, then that allowed rungs later on in the program to be scheduled or to be examined, okay? And so that's pretty common. That way, if you accidentally hit the procs and that the internal system is not energized and the procs doesn't start doing anything. The only difference that we noted was that sometimes if you have internal M memory, that you would want to have some type of a light on or something like that, indicating that we do have memory internally. We went over the Boolean programming, the ands and the ors specifically, and we went over the math of them. So 2-input AND gate is A times B, and the OR was A plus B. We generated truth tables for these, and we used them in combination. We went over the Boolean concepts of how to take something, a circuit, and you could make it ladder logic, you could make it Boolean algebra, you could make a gate circuit out of it, ladder equivalent, Siemens equivalent, and vice versa. If you have one, you can create the other 2 or 3, or have the math here, you can create ladders, and it all says the same thing, just different ways of looking at it. So what you're looking at right here, by the way, is this could be a holding circuit, A or B. Well, it's close to a holding circuit. A or B in series with C equals Y. This would be, if it was a holding circuit, it'd be A or Y in series with C equals Y. Okay, so we did have memory at the end of the lab. We wanted to accomplish it with Boolean or FBD programming. And so if you want to really take a look at how a memory circuit works, what I was just talking about there, I'd like to stop the video here and take a look at the solutions here for memory, the mathematical and the graphical and the programming solutions of it. All right, conversions of ladder to FBD. Siemens is kind of cool that if you programmed something in FBD and then you went to change programming languages, it would automatically convert it back to ladder logic for you if you needed to see that. Or if you programmed it in ladder and you went to change programming language, it would convert it to FBD. So that's a benefit of Siemens compared to like Allen Bradley, is that you can program in different programming language. Why would you use different programming languages? Well, what we're going to learn about today is function blocks. And they're similar in the advanced Allen Bradley. They're called add-on instructions, AOIs. And so what an FB, when you program in this FBD, maybe it's just easy to see that all inputs on one side of a function block need to be true, and that would cause the output. You don't really, maybe the technician doesn't really want to look inside of the function block to see what the ladder logic is. They just are looking to see, you know, is the safety made, is the overload correct, is the e-stop correct, those kind of things like that. And then you just look for the inputs and see the outputs coming on without having to look at ladder logic. We'll explore that concept a little bit more here. There was homework and quiz from last unit, last module. Be sure that you understand the answers there. The week 9 topics are function block programming, or FBD. Siemens is a nice processor, a nice programming language for using FBD. One of maybe the favorites, that's one of the strengths of Siemens, is the function block programming, the way that it's set up. So a function block, from the reading, you learned that it was basically a graphical depiction of flow. And so what you hear here is a function block, and this is performing a function. Inside of this function block, there's going to be a program. It could be ladder logic program. It could be something that was programmed using FBD. It could be something that was programmed using structured text, whatever. There's a program in here, okay? So it's taking inputs here on the left, and it's analyzing the logic that's in there that we don't get to see necessarily. We don't get to see it here. And then it's giving us an output, okay? So these can be programmed in a variety of different ways. And then when this gets scheduled, there isn't necessarily any power rails. If you schedule it using FBD, it just gets put in. If you schedule it using ladder, then there is a power rail, and we'll go over that. But you can program a function block however you want, and then you can schedule it however you want. And we'll review scheduling a little bit as we go through here. Here are the components. What this is showing is this is a function block that would look in the Allen Bradley control logics, but it's very similar to what Siemens is. Here's our function block, and you're going to bring in values. On some programming software, you actually can connect arrows. With the Siemens, you just can kind of bring this node right to that node, and it connects it. Okay, so it looks like it's taking a couple of inputs here. It's doing some work on it inside of the function block, and then it's returning the value as output. Okay, so those are the basic things of a function block programming. So function blocks, once again, are graphical representations of executable code. Here is, it looks like it's looking like a band, so it's taking inputs on the left here, and there's some code in here. We don't know what's going on with these inputs sometimes to create an output. And in this case, it's a Boolean AND. So in this case, I know that it's an AND, so it'd be input 1 and 2 and 3 and 4 to get that output. And so an AND and the OR is what we did, and those seem to make the most sense, but we'll be creating much more sophisticated functions and function blocks. Here's that Boolean AND right here. So here's, you put the band in, the Boolean AND, and this is the Allen Bradley version of it. The Siemens is just a little bit different, but kind of the same. That you have 3 sensors coming in, and then you have an output. And so if you program this and create this, it's just a ladder logic where you have, you know, a contact, and a contact turning on the output. We don't need to see that. All we need to do is put the band in there, and then this ladder logic doesn't really show up unless you expand the band here. So if you're a technician and you see band, you know that this sensor, and this sensor need to be true in order for this to come on. And so if you are trying to troubleshoot and you don't have one of these sensors true, well, then you know what the problem is. If you look here and you see 1, 1, 1, and you see 1 here, but that's not on, well, then you probably have a burned out light. There's no troubleshooting ladder logic because the technician might not be able to get to see the ladder logic. They just want to see the inputs and then see how that works with the outputs. Here's that Boolean OR from control logic. So we know what's inside of here in the Boolean OR. It's a OR ladder logic is in here, and this is just 2. If we added another input there, we could do 3 or 4 or 5, and then this ladder logic would be modified to have multiple ORs. Okay, so that is a function block. Once again, you just look, if you're a technician, what's going on the inputs to see if you're getting what you want on the outputs. The Siemens and OR looks a little bit different. This is the AND right here, 2, and there's the OR 2 input. If you wanted more, you would just click the little star there, and you could have 3, click 4, click 5, as many as you want, or you could delete it. But you have to have at least 2. And remember that you could tag these up, so you could take, you know, this OR, and you could move it right to one of the output of the OR and move it right here to the AND, and it would then start creating a more sophisticated Boolean gate logic. Subroutines. So a subroutine is a program within a program, and it says it only will run when called, or in PLC terms, scheduled. So my big example, this is the movie The Matrix. If you haven't seen The Matrix before, The Matrix is about a big computer program that simulates the world. And within this computer program, there are the normal things that happen every day. There's people and cars and television shows and everything like that. And that's just all part of the program that's running every day, and that's just life. But every once in a while, within this big alternate world, a computer program, this Agent Smith pops up, and this Agent Smith is a subroutine. And Agent Smith only pops up when he's trying to kill the hero, whose name is Neo. And then after he either doesn't succeed, then that subroutine quits running and it doesn't run anymore. And so Agent Smith can pop up multiple times, but he's not. Agent Smith is not necessarily scheduled. And so in this little clip right here, you can watch Agent Smith replicates himself, and because Agent Smith is a subroutine, you know, let's say Agent Smith had a bunch of ladder logic within describing what Agent Smith did. When you replicate Agent Smith, then all that ladder logic just gets replicated. And so if you've seen The Matrix, at the end there's thousands of Agent Smiths, and instead of having to recode Agent Smith every time, you just call Agent Smith, call Agent Smith, call Agent Smith, call them a bunch of times, and that is the subroutine. So there's a little Agent Smith from The Matrix. So how does scheduling work? So here's a little activity from the worksheet. Go ahead and watch the scheduling example video there. Okay, so now that you understand scheduling a little bit, we're going to talk about these subroutines for Siemens. So Siemens has functions and function blocks, and those are the subroutines. They do need to be scheduled once you create them. A Siemens FC is a subroutine that doesn't have any memory. So once you create the FC and you schedule it to run, it's not going to retain. Every scan, when the data table gets reset, it gets brought back to 0. And even if there was something that was a 1 in there, it'll get reset to 0, and it'll start the scan again, looking to see if the inputs were 1. It's not going to 1 or 0. It's not going to assume that anything was 1. The function block, on the other hand, does have memory, kind of like a retentive timer. And when you schedule the FB, a data block is created. Okay, so every time you take the function block and schedule it, you get a data block, even if it's the same function block. So if we had Agent Smith and we scheduled Agent Smith, 6 times, we would get 6 data blocks. And each data block remembers what is going on with each Agent Smith, because each Agent Smith might be doing something just a little bit different. Okay, and the data block holds the status of the data. So if there is a 1 in there, when the next scan starts, it's going to kind of remember the output being 1 or something retentive. There's a retentive nature of it, and it will apply that to the scan, like in the ladder, like we've learned in the past. If you accidentally delete the data block that was created with this function block, then it's going to act just like a function. It's going to not have memory. It won't remember the status of what was going on. So here's an FC worksheet. I go ahead and work up one on the example video, and you'll see how it's scheduled. I'm going to use the function. I'm going to create one, and I'm going to use it twice, once for light 1 and once for light 2. We'll go into a little bit more about how to use local tags and PLC tags, global tags, in just a minute. So go ahead and watch that video and fill out the worksheet. Okay, so we have local versus global tags. That's what I showed you creating there. So the local tags are used in a subroutine, and they can be duplicated. So if you think about the movie The Matrix again, one of the subroutines was Agent Smith. There was other subroutines that were other agents as well, but he was kind of... Then there were other heroes in the movie, I think like the Oracle and people like that were subroutines. So these subroutines get called throughout the movie, and they could be duplicated, okay, the tags that were used inside of them. And so, for example, the one that I just showed you, I could have used the tag start into a function block, and I could have used that same tag start into a function block again. Or more importantly, I could have used a local tag such as output into a function block, and I could have used the same tag into another function block called output and output and output. And then you might be thinking, well, you said you can't use the same output twice. Well, the local tags, they're not aliased to real inputs or real outputs. So you can use the same name over and over and over again inside of the functions and the function blocks, because the subroutines have nothing to do with each other. They don't know what's happening inside of each function block. Okay? Global tags are different. They can only be aliased once, and the reason why is because, well, if you have a push button hooked up to the PLC, you only have one push button. You can't have more than one push button physically connected to the input module. And you can program that input as many times as you want, but there's really only going to be one push button connected to, let's say, input 1. Okay? And so what a global tag is for I/O, and that you can assign an address to a global tag. Bits, the M bits, they can be created both locally and globally, okay, as well. It just depends on what you want to be doing. If you create a global or a PLC bit, then you should probably only use it once, because it's going to be scheduled into the main program. But if you have a local bit, something like a system memory or something, then you can use it as many times as you want, because once it is in a function block or an FC, the other FCs and the other FBs have no idea what's going on in there. Okay, so let's take a little bit deeper look at OBs and FCs. This is pretty involved here to show you how we create a function block or to do a motor, or function to do a motor, and we're just going to use that function over and over and over again. In the local tags are the same, but we do use different PLC tags that are affecting the function block. So go ahead and watch this video. Okay, so the MCR Basics, there is an MCR connection in the lab. Just wanted to remind you how to do that. We're going to use the normally open contact of the MCR to be wired into the input module. We're going over this a little bit so that when we get to safety relays, you'll have some knowledge of how a safety relay might be used to trigger the PLC that the MCR is actually on. Okay, so the MCR provides the voltage to source, the input module, and input, and I show those connections here if you want to take a look at that. There is a quiz for this unit, and then a lab. The lab is you want to really read and understand how the local and the PLC tags, the global tags, are working as you work your way through it. And the last one is a little more involved, where you want to create a single function block that does all of those things that are listed, and then you're going to have to schedule it twice, because you're turning on either a forward starter or a reversing starter. So there you go. Good luck.